Hold on, let me get the page.
Oh, my car caught on fire. It shouldn't have been oil leak.
Your car caught on
My
fire?
car caught on fire.
Are you
It
serious?
started smoking. So, no, because I went early in the morning, I went to like Target or something. I already forgot where I went. And then as I pulled into the parking lot, it just started smoking.
Diego, that's
So
not.
today I went into the Honda repair thing and they were like, yeah, your car just started leaking oil and it burned in the engine or whatever.
I hate when that happens. Wait, that's not. That's a pretty easy fix.
Yeah.
Okay, so on 32A, here, let me kind of give you a hint of what I'm looking for. So sketch, where did you get that going? Okay. So you got sketch the two plates and the region between them showing the distribution of positive charges on the bottom plate. Complete your diagram by sketching the electric field line. Okay, so here's the deal. So you're told that this top plate is negatively charged, right? So here you have the bottom plate. So what's going to happen to the electrons that are down here in this bottom plate if this is negatively charged? They're going to scurry away because those are little chihuahuas. So what's going to be left behind? So you just need to come in here and go, okay, well that means I'm going to have some positive charges left behind, okay? Now, you've got like this peak, right? So this is what I tried to show you yesterday. So when you have a peak, that's when you have a high concentration of these charges. You're going to have like a lot of positive charges concentrated at that peak, which is why you don't want to stand on top of a mountain during a lightning storm. Okay? So the next thing it says, you want to draw in on B, complete the diagram by sketching the electric field lines between the two plates. So if you put a positive test charge right there, what's going to happen to it? It's going to be repelled by the positive and attracted by the negative. So what I'm looking for is you realize, okay, well if this one would go like straight up, this one would curve a little bit, okay? And then once you get over here, so that's kind of all that you really need to have, something like that on number 32, okay? Just realizing that at that peak, that's where, so imagine if you have like a positive test charge right here, it would go out and then it would curve up towards this. This would curve out and go like this, but then once you get to the flat region, then they would just go straight up. Okay, so that's all I'm looking for on that one. On 38, and 38 was probably the most complicated one just because it was kind of this cross-disciplinary thing. So you've got to use conversions of millimeters into meters. Keep in mind that a 2 millimeter diameter, okay, which is about like if you've ever seen like a BB shot, okay, that's about all this is. So you've got to find the mass, and then you've got to use the molar mass of copper, and then you've got to use Avogadro's number, and then you have to look at copper and go, okay, wow, that's the number of electrons on a copper atom, which is 29. There's 29 electrons per atom, that's the atomic number. So you need to find like the total number of electrons. And then you need to figure out how many electrons it takes to create a 50 nanocoulomb charge. And then finally, you need to take the number of electrons that are on the carbon atom and then look at that as a ratio of the number of electrons it takes to create the 50 nanocoulomb charge. And the whole key to that is that it says, what is the fraction of the electrons? So that's going to be like a decimal. It's going to be a very, 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 very small number of the total number of electrons. So that's why I said that answer to number 38. And so help me, make sure that you can go through and do all this math. There's some say, hey, what'd you get for 38? And then just write down the answer, because if all you have is the answer, I'm just not buying it, okay? When you have all these different calculations to do of mass and density and you're stoic and everything else. So, anyway, so there's that one. On 64, that in nanocoulombs should be around 750. Okay? Now, I want to make sure everybody's kind of cool about, you know, all of these problems like on 65, 66, because this is what you're going to have to be able to use on the lab. Okay? So, and this is kind of what we talked about yesterday, is that when you have this balloon, and it's out here at an angle, and this is what you're going to do in the lab, you're going to have your gravitational force, you're going to have your electrical force, and then if you know this angle, then you can figure out like the tension and all this other stuff, okay? So your answer to 66, that angle should be around 15 degrees, okay? So ish, but it should be around 15. And on 68, with that one, you want to figure out how high above should it be for these forces. Basically, you're going to set these two forces equal to each other. So on 68, on a weighted GPA in centimeters, it would be a really, really good GPA. On a weighted GPA in centimeters, like probably not even possible, but yeah. If you could pull that off, that would be really, really, really cool. So, maybe on a 6-point scale, how about that? So,
Yeah, I was gonna say.
anyway, so it should be around 5, by the way, in case you haven't figured that one out. Okay. Are there any specific ones you want me to work? Or get you set up on?
Do 65.
Huh?
65.
Okay? So, on 65, here's the deal. You have the value of the electric field, right? So, you've got that pushing over to the right. You've got your angle, that's 20 degrees. And then you got a 5-gram ball, so that's going to be 5 grams. So right away, since you know it's a 5-gram ball, what else, then what can you find? Yeah, you can find the weight of it, right? Okay? So you can find the weight of that pushing up. Now, you're also told on this one that you want to find the charge on the ball. So you, at the end of the day, you want to find some number of coulombs. So here's the deal. So you can, knowing that once you find that weight, okay, which is going to be like 0.049 newtons, so then at the end of the day, you want to use FEC, because of the fact that once you know the strength of that electric field, okay, so F equals FEC. So what you want to find is how, if you can find that side of the triangle, the force that's actually going to push that out. They gave you the electric field strength. So if you can find this side of the triangle, that's the force side, and you got your electric field strength, then it's just a matter of solving for Q. So you just got to do a little bit of trig, maybe a little bit of tangent action to figure out the value of that electric field. Then over your electric field strength, so then you're going to know your force, then you know your E, then you can solve for Q. Okay? Anything else at all? We're good? Going once? Twice? Solid. Okay, so get those. So, Mr. Carter, stop that for a second. Here's what's going to happen in this lab. You got 2 days, okay, today and tomorrow, to do this lab. There's 16 of you. Well, Amanda's not here, so let's assume that there's actually 16 of you. So I want 4 groups of 4. Okay, figure that out, how you do your groups of 4. I don't care, but I want 4 groups of 4. So here's what you're going to do. You can pick whichever color balloons that you want. Lauren, you can name the balloons
Yes.
however you want to name them, okay? You can label them A and B, you know, whatever you want to name them, okay? If you just want to number them, I don't care.
Can we give them African names?
So you need to collect whatever data that you need to collect to figure out all of this information that you want. So here's going to be the technique, okay? You're going to blow up the balloons. One of the things you're going to have to calculate is the gravitational attraction between the two balloons, okay? Center distance. To do that, obviously you're going to have to know the mass of each balloon. This is where the buoyant force calculation comes into this thing. Because when you put this balloon on the scale, okay, are you getting a true measure of the gravitational pull on that balloon?
No.
No. Is your reading on the scale, is the mass actually bigger or smaller than what you're reading on the scale? The actual mass.
Oh. Never mind, sorry.
So imagine this. Let's say that you're standing on a bathroom scale and you're underwater. Is that bathroom scale going to be bigger or smaller than what it is if you were just standing in air?
Small.
Be smaller because you have this buoyant force, right? Okay. Now remember, the buoyant force is equal to what? Well, basically, it's going to be your buoyant force, remember, is rho v g. Okay, that's the value of your buoyant force. Obviously, to do that, you have to know the volume of the balloon. Now, what you can do, blow it up sufficiently. It's not perfectly spherical, but if you can measure the diameter, you can kind of get an idea of what that, you can just assume that it's spherical, okay? So, you can find the volume of your balloon. I've given you the density. Get off to the races from there. So I'm going to have a scale in the back. You can put that on the scale. Get your numbers. Keep track of each one. Now obviously this is all going to be about the data. Okay? You're going to hand in one per group. It's going to be typed. This is kind of like your cumulative lab final. Okay? I want to be impressed. I'm not going to guess any calculations that you have done. Okay? I want to see the equations. I want to see the conversions. I want to see the units. You're only handing in one per group. So make sure that it's done right, okay? So you're going to get your preliminary data, okay, whatever you need. Then you're going to take a piece of light thread, and there's a couple of ways you can do this. Some people like to tie one big long string, and I've got like in the back or up here, I've got like hooks that you can hang it over a hook. So what you want to do is you want to charge the balloons. I'm going to have some blankets and stuff floating around, and you're going to charge these balloons. Now the humidity is a little bit higher than I like, but there's not a lot I can do about humidity in the room. Because this works better if the air is really, really, really dry, but we've got the system coming in, so the humidity is a little bit higher than I like. But basically what's going to happen is that you're going to charge each balloon, okay? And then imagine that this is suspended by a string. And then what's going to happen is that these balloons are going to push off of each other. Okay? And then that's going to be hanging down. I'd have these strings down to about yay. Okay? You don't want them right up there to the ceiling. You want them as far down as you can, you know, I'm not saying all the way down to the floor, but at least have them longer than like this, down to about here. So you're going to have these balloons like this, and they're going to reach a point of equilibrium. Now, there's a couple of challenges. Number one, and this will lead to your frustrations, because as soon as you get close to it to try and measure things, guess what? You become part of the system, and you disturb it. So you want to find a way to make these measurements without you disturbing the balloons too much. Okay? Good luck with that. That's going to be the most challenging part. So I don't care what you measure. Some people like to measure the angle up there. Some people like to measure the length of the strings. Some people will tie like well, they'll make like 2 strings. They'll tie 1 string here, 1 string there, they'll make them the same length, and then they'll do this. That way you'll know exactly what the length is. I don't care, okay? This is up to you on how you take on this challenge, all right? What you do with this is up to you. But, so you're going to have all these different calculations to do, and then I'm going to actually set up a big table on that back whiteboard, and then we're going to compare everybody's numbers to see how this deal plays out, okay? So, I'm going to have a bag of balloons over there. I'm going to have blankets. Some blankets work better than other ones do as far as doing the charge thing, okay? But yes, the balloons are negatively charged, okay? You know that. We know the balloons are negatively charged. So there's a whole bunch of things and calculations that you have to do. You can assume, obviously, that the forces should pretty much be the same on each balloon. So there you go. I'm done. Good luck. This will be due at the beginning of class on Friday. The test over all of this is going to be on Tuesday of next week, okay? Because we've got one last unit to do, kind of a summary thing on an assignment on Friday. Unfortunately, then we have spring break, and then we're going to come back, we'll review on Monday. I'll try and reteach you everything that you have learned, and then we'll have the test on Tuesday. Okay, so at least I'm not making you have the test right on that first day back.
I was like, please don't say Monday.
No, it's not, no. The test will be on Tuesday, so that'll give us Monday to relearn all this stuff,
Are we
okay?
gonna have like a midterm?
Huh?
Are we gonna have like a midterm?
I don't know yet. I gotta see how things are going. So I'd really like to, but I don't know. We'll see. So